Hello, welcome back to the BC Calculus online video tutorials for Mr. Billingham's AP Calculus class. The material in today is covered on this year's AP exam content, so you do need to learn this. So the major thing in this section is called the ratio test. So remember last time in the last video we talked about the direct comparison test? For two non-negative series, we learned that if term by term each an is less than each bn, and of course since they're non-negative they're both greater than 0, if the sum of bn converges, then an converges. And similarly, if sum an diverges, then sum bn diverges. This should be pretty obvious, I think. In this test, the direct comparison test, we compared the terms of one series to the terms of another. In the ratio test, we'll compare the terms of a series to other terms, the immediately preceding terms in the series. So we're looking within the series to compare the terms rather than between two series. So as I said, the ratio test is a pretty important theorem, very, very useful, and it is on this year's AP test. So imagine I have a series with positive terms, and the limit of the n plus 1th term over the nth term is some number L. Then the series converges if L is less than 1 and diverges if L is greater than 1, and this test is just not conclusive if L is 1. So why does it work? Well, suppose the limit L is 0.9. Well, that means it's trapped term by term beneath a geometric series with a ratio of, say, 0.91. And that means that since the geometric series converges, this series would converge. Similarly, if the L is greater than 1. So we'll take a look at an example of using this. The ratio test not only tells us whether some series converge or diverge, but it also allows us to find the radius of convergence. Let's look at an example. So our task here is to figure out what's the radius of convergence of the infinite series nx to the n over 10 to the n. All right, so to do that, we want to look at the ratio of the n plus 1th term to the nth term. Notice that so far what I've done is I've written out the n plus 1th term over the nth, and then I've divided those two fractions by multiplying by the reciprocal. In the future, I'm going to go straight to this step. So instead of finding the ratio a n plus 1 over a n, I typically will find the product a n plus 1 times the reciprocal of a n, and that's going to save us some time. But let's regroup and see what we can do with this as we take the limit. So it simplifies down to n plus 1 over n times x over 10. Now in the ratio test, what you want to do is you want to take the limit of the absolute value of that expression. And what we're going to do here is we're going to set the limit less than 1. Now we know the limit of n over n plus 1 is 1, so the problem becomes absolute value of x over 10 is less than 1, which is the same as the absolute value of x is less than 10, which means the interval of convergence is negative 10 to 10. We can check the endpoints here. If x were 10 or negative 10, then the limit would be 1, and this would be an inconclusive test. And so what you'd have to do is actually plug that in, and we'll look at handling the endpoints later on in this section. But if I plugged in x was 10, then x to the n over 10 to the n is just always 1. And so in that case, the series becomes sum from k equals 1 to infinity of k, and that pretty clearly diverges. I'm not sure if you remember it, but in the last video we looked at a theorem that said for any powers series centered at A, there were 3 possibilities. One was it converged for all real numbers, which had an infinite radius on either side of it, A, and examples of that you should know: sine of x, cosine of x, e to the x. Or there was some finite radius r, like in the last example where the radius was 10, and so it converged from negative 10 to 10, positive 10 would be the interval of convergence. And the last case it mentioned was that it only converged at A, and that meant that the radius of convergence is 0. And it's kind of an odd thing, but let's take a look at an example of that. The title of the example gives away the answer, but let's go through the math. So again, I'm going to look at the limit as n goes to infinity of the n plus 1th term over the nth term, and typically, well, in this case, it's pretty easy to just do that. And remember, we look at the absolute value. So here I've simplified n plus 1 factorial over n factorial. The only thing that's left is the n plus 1. You wind up with n plus 1 times x, absolute value of that. Now if x is 0, then the limit is 0, and clearly that converges. But if x is any number at all besides 0, then n plus 1 times that number will grow without bounds, and the limit will clearly be greater than 1, and this will diverge. So this is a series that only converges at x equals 0. Let's take a look at another little exploration related to this. I feel like we've done it before, but we'll go ahead and do it. So we have a very interesting series that comes out of integrating 1 over 1 plus x. So this is the series for the natural log of 1 plus x. We've looked at it before, we've played with it before, but we're going to do several things. We're going to apply the ratio test to determine the radius of convergence. We're going to substitute left and right hand endpoints of the interval, and then try to figure out whether the resulting series converges or diverges. And we're going to talk about whether it converges absolutely at the right-hand endpoint. So let's get rid of this material on the screen and go through those steps. So here's the series we're looking at, and the first task was to use the ratio to determine the radius of convergence. Again, as I mentioned I would, instead of first dividing then multiplying by the reciprocal, I just did a sub n plus 1 times 1 over a sub n. Now the first thing that I can do pretty easily, because I'm taking absolute values, those negative 1 to the n minus 1 and negative 1 to the n's cancel, and I wind up with limit as n approaches infinity of x to the n plus 1 over x to the n is just x, and then it's times n over n plus 1. The limit of n over n plus 1 as n approaches infinity is 1. And so the limit as n approaches infinity of an plus 1 over an is the absolute value of x, and by the ratio test, this will converge when that ratio is less than 1. So the interval of convergence is negative 1 to 1. Now, the second thing they want us to do is substitute the right and left-hand endpoints into this series. So if I substitute the right-hand endpoint in, I get 1 minus 1/2 plus 1/3 minus 1/4. And you remember that this meets all the criteria of the alternating series test. The terms alternate in sign, each one's smaller than the one before it, and they have a limit of 0. And so when I plug in the right hand, it does converge there. So the interval of convergence includes the right hand endpoint. What happens when I substitute -1 in? Well, I'll get -1 minus a -1 squared over 2 is 1/2, then minus 1/3 minus 1/4, and this is the opposite of the harmonic series. And so I hope you remember the harmonic series diverges. A quick recollection of the proof: we showed that 1 all by itself was at least a half all by itself is at least a half. The next two terms, a third and a fourth, are each at least a fourth, and there are 2 of them, so collectively they're at least a half. And you can keep grouping this into bunches of terms that each add up to at least a half, and so it is equal to an infinite number of at least a halves and diverges. So what we know is that this series diverges at -1, but it converges at 1. But if I take the absolute value of the expression that of the terms that I get when I plug in 1, that turns into the harmonic series. So this series converges at 1, but not absolutely. So this is an example of a series that converges conditionally at 1. Well, we'll have just a couple more examples, and we'll finish out the chapter and the section, or finish out the section, not quite the chapter. Here we want to figure out whether the series sum from 0 to infinity of 3 to the n over 5 to the n plus 1 is converging or diverging. They suggest doing it by the ratio test. Since everything is positive, there's no need to look at absolute values here. The limit is 3/5, and so since that's less than 1, I prove that this converges. I'm going to suggest an even easier way is to use the direct comparison test. Term by term, every single one of these terms is positive. And secondly, 3 to the n over 5 to the n plus 1 has a slightly bigger denominator than 3 to the n over 5 to the n. So term by term, I know the following. And since I know that the sum of the series 3/5 to the n converges because it's geometric with the absolute value of r is less than 1, I know that the original series here converges. I would suggest that in this case, the direct comparison test is a little faster than the ratio test. All right, one more very cool example, and then we are done with the section. This is called summing a telescoping series. And the reason it's called summing a telescoping series is because the expression 1 over n times n plus 1 in the denominator can actually be broken into partial fractions. And that means that we can write out the whole series as follows. And what happens is that the minus a half and plus a half cancel, the minus a third plus a third cancel, and so on. So in any partial sum, let me write this out. In any partial sum of the expression up to n, all the middle terms cancel, and it adds up to 1 minus 1 over n plus 1. And the limit as n approaches infinity of 1 minus 1 over n plus 1 is of course 1. So this infinite telescoping series adds up to 1. And the reason they call it a telescoping series, well, you've probably seen an old pirate movie where a pirate pulls out this collapsed telescope and snaps it open. And what happens is all the, after you break it into partial sums, they collapse and you only wind up with the first and the last term. So I think that's kind of a fun example. Anyway, hope this was clear. This concludes 10.4, getting close to the end of all the material for the year. Again, this topic is on the AP test for this year, the ratio test. It is important. Please stay healthy, stay well. I am going to invite you all to a video conference, an open classroom using Microsoft Teams on Tuesday. I think I'm going to do that at, let's see, somewhere a little after noon, something like that. But please make sure you have Microsoft Teams installed. Also, go out and get Microsoft Whiteboard. And when you register for it, log in with your jesuitcp.org email or account that you were given. So stay healthy, stay well. Please let me know how you're doing, and talk to you soon. Bye-bye.